And let's finish up the formulation of the theory for small displacement gradients. So what we have in mind here is the theory in which the displacement gradient is small. So the deformation gradient is approximated by this shifter that we introduced. We neglect the displacement gradient. We don't want to neglect it entirely. We just want a theory that's valid for small displacement gradients, an approximate theory. And, and consistent with that, we'll assume that let me rephrase that. The displacement gradient deviates only slightly from this shifter we introduced. We'll also assume that the plastic deformation deviates only slightly from the identity. So with h equals fk, that means the elastic deformation is really also a two-point tensor, which we'll assume deviates only slightly from the shifter that we introduced. So we'll assume that, if you can think of the shifter as a kind of generalized identity, we'll assume all the elastic and plastic deformations and the total deformation deviate only slightly from the identity. Okay, so let's proceed with that discussion. So when we're assuming small displacement gradients, that doesn't mean the displacement itself is small, because of course a small derivative doesn't imply that a function itself is also small. We'll assume small displacement gradient. So suppose that the maximum over the entire body of the displacement gradient, then that will be some function of time, call it epsilon, and we'll suppose that it's always, for all time, much less than 1, for all time in the interval under consideration. In Cartesians, the norm of the displacement gradient is just these sum of the squares ui comma a square root. And so this epsilon then would be the maximum of that over the body, which is greater than or equal to the value at any point in the body. And since this is the sum of squares, it's greater than or equal to the square of any one component, let's say. And so the magnitude of any one component of the displacement gradient is bounded above by this epsilon, and therefore much less than 1. You can, of course, replace the u1 comma 2 by any other fixed index I and fixed index a, so that all the displacement gradient components in in a Cartesian system, let's say, would be tiny compared to 1 by assumption. The shifter, on the other hand, these are cosines, direction cosines, if you recall. They are order 1 in magnitude. So the strain displacement relation we had derived, in Cartesian form, would be approximated by this expression here, where we neglect the squares, ui comma a, ui comma b. So this would be the leading order strain displacement relation under our assumptions. In a coordinate-free form, that would be this. The actual strain is approximated at leading order by this square bracket here, which involves the shifter and the displacement gradient, which is, again, is a two-point tensor. Okay, that's the referential displacement gradient. In other words, grad u maps d capital X onto du. We could also define a spatial displacement gradient. I'll use this notation to be such that it maps d small x onto du. So then we can relate the capital G grad u to this spatial displacement gradient. We have this here, chain rule for calculating the referential displacement gradient. Here's the spatial displacement gradient. The small x is f d capital X, of course, and so capital G grad u is the spatial displacement gradient times F, excuse me, F is the shifter plus the same referential displacement gradient. We're neglecting capital G grad U in comparison to the shifter. Then this capital G grad U is approximated in this way in terms of the spatial displacement gradient multiplied on the right by this shifter. And that implies that the norm of grad U is also order epsilon. It's a very small number. In Cartesians, this would be simply ui comma a is ui comma j xj comma a, just the chain rule. Xj comma a is the deformation gradient component, ja. Insert what that is in terms of the shifter and the displacement gradient. Neglect this compared to these in accordance with our assumptions, and you just get the component form of this equation here. You can see that the tensorial character of the equation is preserved because this is a two-point tensor. This is spatial tensor multiplied on the right by a two-point tensor gives you a two-point tensor in accordance with this index notation. Okay, in the expression for the strain, we require the shifter transpose capital grad U and likewise capital grad U transpose times the shifter. So then those are approximate. So I'll use this wavy equal sign to indicate terms that are valid if we neglect grad U in comparison to the shifter. We get these. So we need to add these together to get the strain. When we do that, we can factor out the one transpose on the left, the one on the right, and in between we get the symmetric part of the spatial displacement gradient. And that's called the infinitesimal strain tensor. And conventionally, in the literature, say in linear elasticity, for example, you'll see people writing this equation without the shifter. Unfortunately, then when you do that, you destroy the tensorial character of the equation. So we really need the shifter here. For example, under superposed rigid body motion, well, let me rephrase that. This epsilon is a spatial tensor, the sum of spatial tensors. The one transpose shifts us from the spatial vector space to the referential one, and the one does the opposite. So this object now is taken all together as a referential tensor, mapping the vector space E, referential vector space, into itself. And that's exactly the kind of tensor that capital E is, the Lagrange strain. So our approximation has not destroyed this essential tensorial feature. We've preserved the tensor structure of the equation. And that's all important, as it turns out. For example, under superposed rigid body motions, we know that grad U plus, for example, is Q grad U, where Q is the rotation associated with the superposed rigid body motion. This is exactly equal to spatial gradient U times F. And grad U plus would be the plus version of that. F plus, of course, is QF. Compare this side to this side and multiply on the right by F inverse. F is invertible. You simply get Q spatial gradient of U is the plus version of that times Q, or in other words, the plus version of spatial gradient U, that is after superposed rigid motion, is equal to this. That convinces you that this is indeed a spatial tensor, because grad U. And therefore, epsilon, that'll satisfy the same condition. If you look at the transpose here, you get the same thing with the transpose here. Add them together, you get this. So epsilon is a spatial tensor. when you operate with the shifter, as indicated above here, write the plus version of this equation. Okay. Then write that the shifter plus is Q times the original shifter, transpose that, put in this expression here. Q is a spatial rotation, so Q transpose Q is the spatial identity, times epsilon is just epsilon because epsilon is a spatial tensor. Q transpose Q again, spatial identity times 1 is 1, the shifter. So you get back to this, which is our Lagrange strain. So we preserve the invariance of the Lagrange strain. Okay, and you can see that the conventional identification, or the conventional approximation, that the strain is approximately this infinitesimal strain as we've defined it, without the shifters, this restriction, this requirement here would be violated. E plus would not be equal to E anymore. It was essential to have these shifters participating in the formula in order to guarantee the invariance of E itself, the strain, under superposed rigid motions. And this violation in the standard, say for example in linear elasticity, this is what leads to the erroneous conclusion that linear elasticity is defective in the sense that it's not frame invariant. And you might wonder how professors could then sleep at night with this problem, right? Because we've been teaching courses on linear elasticity forever. And without resolving this issue, we're concealing a significant flaw in the formulation. So that's why I've harped on, I've made an issue out of this shifter business. Okay, the stresses, Piola stress, say this is relative to the reference configuration, likewise second Piola-Kirchhoff. They're related this way, as you know. F, put in the relationship between F and the displacement gradient. If we neglect grad U in comparison to the shifter, as we've indicated, then the Piola becomes essentially a shifted version of this second Piola-Kirchhoff. You can see that's sensible because Piola is a 2-point tensor. This is a 2-point tensor, referential tensor. The product gives you a 2-point tensor in accordance with this Cartesian index version of the same formula. Cauchy stress, we know that's JT is FSF transpose exactly, where J sub F here means the determinant of F. F is approximately the shifter, so we put that in. Det F, we need to approximate that. The easy way to do that is to remember that the square of det F is det C. C we had last lecture in terms of the shifter and the displacement gradient, and there was a referential identity here being added. So we can write C as the identity plus everything else, call it capital A, which capital A is the terms involving the displacement gradient. And under our assumptions, capital A is order epsilon, very small in magnitude. So the square of det F is the det of this identity plus A. And to remind you how to work that out, let's write that as det A minus lambda times identity with lambda equal -1. Because that this determinant, you remember from the continuum mechanics, the characteristic equation for the eigenvalues lambda of a tensor, of a symmetric tensor. Minus lambda cubed, I1, the first invariant of A times lambda squared, the first invariant is the trace, minus the second variant times lambda, third invariant, which is the determinant of A, all evaluated then at lambda equal -1. And we just need to approximate this for small norm A. So the first term, so this -1 cubed gives me a 1 squared, trace of A, and then everything else is higher order. I2 is order epsilon squared. I3 is order epsilon cubed, so we just want the leading order approximation. The trace of A itself, if you take the trace of this and neglect this in comparison to this, because this is order epsilon squared, this is order epsilon, you will get this with an error of order epsilon squared that we're neglecting. This, however, grad U is spatial gradient times 1, etc. So we can factor out a 1 transpose in front and a 1 in back. When we take the trace, because the shifter is orthogonal, it's not going to affect the trace. We can put the 1 in front and we get 1, 1 transpose, which is the spatial identity, and that doesn't affect the trace. And then this is just twice the infinitesimal strain tensor, the trace of that. And we neglect terms order epsilon squared. So if you take the square root of this, you just replace the 2 by a 1, because if you square this, you will simply get this, provided you neglect terms of epsilon squared. In the same way, the reciprocal will just be 1 minus trace epsilon plus terms of order epsilon squared. You can verify that just by multiplying these two together, and you'll get the number 1 if you neglect terms of order epsilon squared. So the Cauchy stress then, at leading order, this is just the number 1. In other words, this is tiny. This is order epsilon, negligible compared to 1. So this becomes, Cauchy stress just becomes the fully shifted version of the second Piola-Kirchhoff stress this way. So in components, that would be this. You can see the shifter plays an essential role in preserving the index structure in a Cartesian representation. It plays an essential role also in preserving the tensorial structure of the equation. So for example, under superposed rigid motions, we know that T goes to QT transpose, whereas S, it remains invariant. 1, however, goes to Q1, 1 transpose goes to 1 transpose Q transpose, and this formula would guarantee then that T goes to QT Q transpose. If you neglected the shifter, you'd get rubbish, right? You get S being invariant on the right, and T not being invariant on the left, so that you would destroy the equation. Okay, so in other words, a rigid motion would simply be enough to invalidate the equation. Okay, so we want to estimate the equation of motion also, let's say the Piola form here, spatial, the referential divergence, referential mass density, acceleration, and so on. In components, Cartesians, that's this. We could easily convert this referential divergence to a spatial divergence. That would be, that's easy to do. You know how to do that. Let's do it in Cartesians just to save time. The Pi A comma A would be this. Use the chain rule to write that as this spatial derivative. Then you need the deformation gradient, approximate it by the shifter. The shifter is uniform, so we can sneak it inside the derivative, and we get this approximately. This, however, this combination is our approximation to the Cauchy stress, and this is just the comma J, the spatial divergence. So the approximate equation of motion is the spatial divergence of the Cauchy stress is this, but the difference between this and the conventional statement of the Cauchy equation of motion is that the mass density now is the referential mass density, which is fixed. Okay. Something I might have done before this discussion about stress, while we're still on kinematics, is look at the polar decomposition of the deformation gradient. You can factorize that into a rotation and a stretch. The rotation is a 2-point rotation tensor. The stretch is purely referential. Okay, and that comports with this equation. 2-point times referential equals 2-point. That makes sense. write f in this form with the displacement gradient, write that in terms of the spatial displacement gradient, then invoke the approximation that f is approximately the shifter. And let's see, that's a bit awkward. What I'd like to do is factor out a shifter on the left. So I can do that by writing the spatial displacement gradient as the spatial identity times that, and write the spatial identity as shifter times shifter transpose, and then factor out the shifter on the left, and I get this. And then this object converts the spatial displacement gradient into a purely referential tensor, which can then be added to the referential identity. So that's an approximation because we've approximated f by the shifter. Okay. So normally, you have to, given a deformation gradient, you have to go through some arduous ordeal to carry out a polar decomposition explicitly. You have to solve an eigenproblem and so on in general. Here we can evaluate the factors more easily by invoking our assumption of small displacement gradient. Let's see how that works. Well, the square of u is the right Cauchy-Green tensor, which is referential identity plus twice the strain, exactly. The strain is approximated by the shifted version of the infinitesimal strain tensor. This, under our assumptions, is very small in magnitude, order epsilon. So the square root of this equation, that would give you u, positive square root, positive definite square root, is just I plus the same thing without the 2. I just put a 1 here. The reason being is that if you square this and neglect terms of order epsilon squared, you'll get exactly this. Likewise, this is immediately, and you can get the inverse immediately. So I should write here plus terms of order epsilon squared, but I'm being lazy about that. The inverse, again, is just replace the plus by a minus. The reason being is if you multiply these together, you'll get the referential identity if you neglect terms of order epsilon squared. Excuse me. So now that we have u inverse, we can evaluate or approximate the rotation factor in the polar decomposition. Here's our approximate f, then we post-multiply by u inverse, which is this. Carry out the product, and you get approximately this, where omega is the grad u minus the epsilon. And we're neglecting terms of the size of the square of norm grad u. That grad u minus epsilon, as you take the spatial displacement gradient, subtract its symmetric part, what you're left with is the skew part. We could call that the infinitesimal rotation tensor in accordance with classical nomenclature. Okay, that's the skew tensor, obviously. And it follows immediately then that this object here, 1 transpose omega 1, is also a skew tensor. That's easy to see because the shifter is orthogonal, so, well, it just follows immediately. So that's also skew. And you can check now if you take the transpose of this and multiply it by itself and neglect terms of order epsilon squared, you will get the referential identity. Okay, so indeed, we've constructed a tensor that's orthogonal then at order epsilon. Okay, well, a small displacement gradient, that is saying f is close to the identity, doesn't say anything about the plastic deformation at all, right? The plastic deformation is not the gradient of anything, so the foregoing discussion here about displacements is not going to be of any help to us. Nevertheless, it's of interest to look at a theory in which, say, the plastic strain is close to zero. Let's have a look at how that works. Okay. So we stipulated before that if we're going to retain the elastic strain in our theory in discussing the overall strain, then for consistency, the plastic strain should be small of comparable order to the elastic strain, which is always small. So let's investigate that. Let's polar decompose G, the plastic factor in the deformation gradient, and I'll use subscript G to identify the rotation factor and the stretch factor. So this RG has nothing to do with the previous R, and the UG has nothing to do with the previous U. There's simply polar factors in the decomposition of G. G, remember, by assumption, has positive determinant, so this RG will be a rotation, and UG will be positive, definite, and symmetric. If you go back in the course, we demonstrated previously that G is actually invariant under superposed rigid body motions. So it's entirely consistent to regard G as a purely referential tensor. It maps the vector space E that we described yesterday or last time into itself. And that's consistent with the decomposition of F. For example, write F is HG in index form, Cartesians, that would be this. For consistency, there has to be an I on the H, and then this Cartesian form. So in other words, G has two Cartesian indices that are both capitalized. Okay, so for this tensor G, we will not require a shifter because it's not a two-point tensor. H, however, will have to then be a two-point tensor such that F is a two-point tensor. But G is purely referential, so our discussion about G will not require the so-called shifter. We know that the square of UG, that's the right Cauchy-Green deformation based on G, that's identity plus twice the plastic strain from the definition we had last time. Okay. Let's assume that that plastic strain is very small in magnitude. Then the square root of this will just be this, for the same reasons we said before. You square this, you'll get this if you neglect squares of this normal plastic strain. The inverse, again, just replace the plus by the minus, and you get an expression valid to leading order, or to the, if you neglect terms of the size of the square of the plastic strain magnitude. If you remember the flow rule, that flow rule specifies this combination, G dot G inverse. That was lambda df ds, where f was the yield function, if you remember. So let's work on G dot G inverse using the polar decomposition of G. Just take the dot of G and then multiply by G inverse. Here you're going to get a skew object, R dot R inverse, and then we're going to have this stuff here. At leading order, so this, we won't approximate this term, just carry it down. UG dot is approximately E dot plastic, and UG inverse is approximately that. Neglect E plastic in comparison to the identity, and you just get this last line here. Okay. Okay. In line with our small displacement gradient assumption, that led us to the conclusion, remember, that the rotation in the polar decomposition of F is close to the shifter. So the rotation minus the shifter is very small in magnitude. In this case, because there's no shifter when you talk about the plastic deformation, The corresponding assumption would be that the rotation of the plastic part of the deformation gradient is close to the referential identity. And as before, that means Rg minus the referential identity is approximated at leading order by a skew tensor. We'll call it omega sub p for plastic. You can then verify that if you take the transpose of this and multiply it together with this, you'll get the referential identity if you neglect terms of the size of the square of this norm. So that's essentially the same discussion we had before. So if you neglect this small quantity in comparison to the referential identity in here, then you get G dot G inverse is approximated by a skew tensor, which is this. We call that before, we call that the plastic spin, plus the material derivative of the plastic strain. And this thing, omega, then, is approximated by small omega p dot. Okay, so altogether, remember, if you go back to yesterday, or Tuesday rather, to equation 1, the strain is exactly equal to G transpose elastic times G plus E plastic. The strain is approximated by this, where epsilon is the infinitesimal strain tensor. G itself is approximated in this way. Right? This was Rg was this plus this, and then U was identity plus this. If you multiply those together and neglect products of EP with omega p, because both are so small, you get this. And then these combine, they're negligible in comparison to the referential identity. So this is approximated by the elastic strain. So we have this approximate decomposition of the strain into elastic and plastic parts, and the further approximation that the strain is approximated by the shifted version of the infinitesimal strain tensor. Okay, so EP is the time integrated version of EP dot, which comes from the flow rule, and then there's this plastic spin that we have to worry about. The elastic strain, remember, is the compliance tensor times the second, operating in the second Pure Kirchhoff stress relative to the intermediate configuration. So this S is relative to the intermediate configuration. So let's keep things simple for the moment by invoking isotropy. Suppose we're talking about an isotropic material. Remember, in that case, that the plastic spin can be entirely suppressed in the flow rule. The plastic, because of material symmetry arguments, the plastic spin effectively has no effect on the flow. So in that case, we can suppress the omega in the flow rule and write G dot G inverse as E dot plastic. And if you look back at the flow rule, then you get lambda times df ds. F is the yield function. And lambda is this scalar function that has to be non-negative to ensure dissipation. And if you recall, for the von Mises yield function, df ds would just the deviatoric part of that second Pure Kirchhoff stress relative to the intermediate state. And that's our flow rule, approximate flow rule then. Okay. I'd like to rewrite this in terms of the Cauchy stress if possible, because getting your hands on the intermediate state, so to speak, having access to it, it would be nice if we can avoid that step. So in other words, I'd like to do for this equation what we did in the case of the rigid plastic material, right? So we can do that. If we recall the relationship between Cauchy stress and this second Euler-Kirchhoff based on the intermediate configuration, that involves the elastic factor in the deformation gradient and its determinant. S is, under our small elastic strain assumptions, that's the tensor of moduli operating on the elastic strain. So let's invoke our approximations. H is Fk exactly, F is this, K is G inverse. Write G inverse in this way, that's U inverse R, UG inverse R transpose, R sub G transpose, that's approximated by this product. This product is approximated by differential identity. If we invoke the small displacement gradient assumption and neglect this comparison to this, then H is, just like F, is approximated by the shifter. The shifter times the referential identity is again the shifter. So Cauchy is approximated, so the determinant then is approximated by 1. Cauchy is then, as before, the shifted version now of the second Euler-Kirchhoff based on the intermediate. And we need S itself, so we just pre and post multiply by the inverse of the shifter and the inverse of the transpose. The shifter is orthogonal, if you recall, so that's this. And this operation converts this purely spatial tensor now into a referential tensor, which is how we interpreted the that second Euler-Kirchhoff stress. So then we need the deviatoric part of S. Insert our approximation here, that's this. Write out the deviatoric part, longhand, that's that. We have here the referential identity because this is a referential tensor altogether. Let's see, I can write the referential identity as shifter transpose times shifter, and I can write the shifter as the spatial identity times the shifter. And then I've just got a square bracket here, which is the deviatoric part of the Cauchy stress. So the deviatoric part of S is approximated by the shifted version of the deviatoric Cauchy stress. Put that in the flow rule and we get this. Okay. So this is the approximate flow rule. And this is entirely consistent with invariance under superposed rigid motions. EP, and therefore EP dot, doesn't change under superposed rigid. Tau does, but then the shifters bring them back, and so the net result is invariant under superposed rigid motions. So we're constructing a frame invariant small deformation theory here. So I've got some information in the decomposition of the strain into elastic and plastic parts. Let's remember that the elastic strain is related to S in this way. We'd like the inverse of that. We'd like to invert that so that we can add the elastic strain to the plastic strain and get the total strain. The first order of business is simply to invert this, and in the case of isotropy, that's very easy. The reason being that the deviatoric response decouples from the spherical response in the case of isotropy. Let's see how that works. If we take the trace of this equation, we get a 3 here, and then we get a trace of E elastic here. So we get 3 lambda plus 2 mu, that's 3 times the bulk modulus times trace elastic strain. If we take the deviatoric part of this equation, of course, that's a linear operation. So the deviatoric part of the sum is the sum of the deviatoric parts, and this first part has no deviatoric part since it's purely spherical, and we just get this. So the trace and the deviatoric parts of the equation decouple. And if you remember from an earlier discussion we had some time ago, the strain energy of the material, which is this quadratic function of the elastic strain, that's positive definite if and only if the bulk modulus is positive and the shear modulus is positive. So we can divide by the bulk modulus here and divide by the shear modulus here. So now we have the inverses of the spherical response and the deviatoric response. We simply add them together to reconstruct the total strain, and we get this. So the 1/3 here, 1/3 gives me a 1/9 times the bulk modulus. I'd like to write this if possible in terms of the Cauchy stress. Well, deviatoric S I've written as a shifted version of deviatoric Cauchy. And the trace of S, well, that's S is essentially the shifted version of Cauchy. The trace, the shifter disappears when you take the trace because the shifter is orthogonal, and we get this. And we can factor out the shifter on the left, transpose, and the shifter on the right if we remember that the shifter is a spatial identity times the shifter. And then in the curly bracket here, the bracket is a purely spatial tensor involving the Cauchy stress alone. Put the shifters on the other side and we get the same thing here, the curly bracket. And if you do a line of algebra, you can rewrite that in this form. So this is the explicit inversion of the shifted version of the elastic strain, shifted to the vector space E star, which is where the Cauchy stress lives, right? Cauchy stress is purely spatial. So this operation converts the elastic to a spatial tensor. Okay, so we have that. Most of the time you see this relation expressed in terms of the engineering moduli, so-called, the Young's modulus and the Poisson ratio, so it can rewrite that here. And with some algebra, too much algebra to do here, but you can verify that these are the same equations provided E is equal to this in terms of the shear and bulk moduli, call that the Young's modulus, and nu the Poisson ratio is equal to this in terms of the shear and bulk moduli. For example, here you can see that if the material is very stiff in its bulk response, so the bulk modulus is very large in comparison to the shear modulus, then you can neglect all the terms involving the reciprocal bulk modulus, and you get nu as approximately a half. Right? That's the incompressible limit. The material is very hard to compress, has very high bulk modulus. Okay, put all this into equation 2, I think we called it. There it is. Right? And we get this, the infinitesimal strain is then approximated. This part we've just expressed in terms of the Cauchy stress. You can think of this as the elastic part then of the infinitesimal strain. And here's the plastic part of the infinitesimal strain. To get it, we have to integrate the flow rule and put the result back in here.
Professor, can I ask you a question?
Yeah.
We said that the Poisson ratio should be equal to 1/2 for the case we have incompressibility.
Yeah.
Since we're in the plastic regime of the deformation, should we take the Poisson ratio in the elastic domain, or should we take that the Poisson ratio is equal to 1/2?
There's no in the plastic part of the response. There's no Poisson ratio. That's a purely elastic concept. Okay.
Okay.
So I'm just saying that if the material is elastically incompressible, then the Poisson ratio would be approximately a half, close to 1/2. Yeah.
Okay, I see.
Yeah. So if you see, there's no such thing as a plastic Poisson ratio or a plastic Young's modulus in principle. Okay. By the way, don't get confused here. I'm using lambda here as one of the so-called Lamé moduli in elasticity. And unfortunately, I'm also using lambda to mean something else in the flow rule here. Lambda is just some non-negative scalar that you have to determine to ensure dissipation. So make a note to yourselves not to, maybe I should have put a lambda bar on the Lamé modulus here. This is called the Lamé modulus. Right? And up here. So please don't make that mistake. This lambda has nothing to do with the one that appears in the flow rule. Okay. And this system of equations here, these are called the Prandtl-Reuss equations. So Prandtl, his actual work pertained to the rigid plastic case, but Prandtl made a suggestion that perhaps, when the plastic strains were small, one should not neglect the elastic strain. So maybe 10 or so years later, Royce actually implemented that suggestion and came up with this formulation now called the Prandtl-Reuss equation. And they arose in response to experiments that indicated that the rigid plastic theory was experimentally off in the cases when the overall strain was small, that there were significant errors in relative to experiments produced by using the rigid plastic model. So the Prandtl-Reuss equations were invented to overcome those experimental discrepancies. You can read about some of that history in the book by Hill and perhaps others. I think now Zach again kindly provided several more books in the meantime, so I'll upload Hill and other material to B courses. Okay, so that's essentially the small deformation theory in a nutshell, equations 3, for the case of isotropy. And almost all the solutions in the small deformation elastic plastic regime are based on isotropy. So there's a large literature associated with this. Quite often, people will express the Prandtl-Reuss equations in so-called rate form, in which you have, just like EP here in flow rule, it appears in terms of its derivative, time derivative. People will often express the entire relationship in terms of a time derivative. But here in this frame invariant form of the Prandtl-Reuss equations, the time derivative is a bit problematic because we don't know anything about the time evolution of the shifter, for example. So as an observer, you're carrying your E star vector space with you. If you rotate relative to the sample that you're observing, then the shifter has a non-zero time derivative. Okay. And however, you can see that this version of the theory with the shifter included is entirely frame invariant, that is invariant under superposed rigid body motions. Without the shifter, it would not be so. By the way, the conventional Prandtl-Reuss equations are always written without the shifter, and so they're not frame invariant. In other words, they're rubbish. You have to have the shifter. So in order to make contact with most of the literature, let's see if we can extract a rate form of the equations. So we start with this approximate decomposition that we indicated. Suppose this is uniformly true for all time. We can take a derivative of it and shift it. The purpose being, we can use the flow rule then to use this flow rule. If you multiply through by 1 and post multiply by 1 transpose, you get simply lambda tau from the von Mises flow rule. And then we have this business here, right? So we have to take an E dot from the elastic relationship, shift it, and take E dot and shift that. Well, let's look at the left-hand side first. You can see that that's approximately the same as the exact rate of deformation tensor. You can work out for yourselves that the symmetric part of the spatial velocity gradient, which is F dot F inverse, that's L, the symmetric part of that is exactly equal to the deformation gradient times E dot, material derivative of the total strain, times F transpose. And you can see if you replace F by shifter plus the displacement gradient and then neglect the small displacement gradient, that this is approximately this. So let's use this exact relationship and approximate that to get an approximation for the left-hand side here. Let's take the dot of F, and a priori, I don't have any reason to say that the shifter is not time dependent. There's no reason why it would not be, because the vector space E star that we talked about last time can change its orientation in principle relative to the vector space E in a time-dependent manner, right? And it would certainly do so. Remember, in a superposed rigid motion, the shifter goes to Q times the shifter. So if Q depends on time, then the rotated shifter also depends on time. Okay, so this is exactly true then. If we neglect grad U in comparison to the shifter, we get this. This thing is skew because the shifter is orthogonal. And then we get this. Referential grad U dot is exactly spatial grad U dot times F. Approximate F by the shifter, and you get this. Shifter transpose is the spatial identity. This is a spatial tensor. And we get this, approximately. If we take the skew part of this, sorry, the symmetric part of this, we'll get rid of this strange term here, right? So D is approximately shifter times grad U dot shifter transpose. I'd like to write that, I'd like to replace that by the dot of something, not just by the shifted version of the dot of something. Let's see if we can do that. Referential grad U is spatial grad U times F exactly. Take the dot of that equation. The referential grad commutes with the time derivative. Right? So you can take the dot first and then take the grad. On the right-hand side, you get the dot of grad U, F plus grad U, F dot. Let's suppose, in addition to grad U being small, that grad U dot is also very small. Okay, so it's a further assumption. Then we can't say anything about one dot in general, so we can neglect this in comparison to one dot. And we get that. On the other hand, grad U dot is exactly equal to the spatial gradient times F, which is approximately this. So we can put this on the left-hand side here and compare it to the right-hand side. And we get this. F dot F inverse now involved grad U dot, which we can get from this equation just by multiplying on the right by 1 transpose. Okay. And we get this. And then we have this part hanging out here. The spatial displacement gradient is small compared to the spatial identity, so we can approximate that further this way. We take the symmetric part to get D. We get the symmetric part of the dot of grad U, which is the dot of the symmetric part of grad U. So we've approximated, and if we then note that D is approximately what we need on the left-hand side of our strain decomposition, then we can approximate this by the dot of something, the dot of this symmetric part of the spatial displacement gradient. In other words, the dot of the infinitesimal strain. And then that's the shifted version of E dot, E elastic dot, plus the part that comes from E dot plastic. Okay, so what remains to be done is to do this, but remember, E elastic, in terms of S, we can take a dot of that equation. I'd like to get that in terms of the Cauchy stress. To do that, I need this. Take a dot of it, you get a lot of terms. H is then, if you go through what we've done before, is approximated by the shifter. So its det is approximately 1. Its time derivative is then approximately the cofactor of the shifter, inner product, the dot of the shifter. The shifter is orthogonal, so its cofactor is equal to the shifter itself, and that inner product is this. This is skew, so that's 0. So we can neglect this term JH dot. JH is about 1. Then we have all this business. The H dot terms approximate H by the shifter, take the dot, you get this. And you can factor out 1 transpose 1 is the referential identity, so you can sneak that in here and you can write that in this form if you like. So let's see, S is given in terms of the elastic strain this way. The premise of the whole subject is the elastic strain is very small in magnitude. So this being a linear function then of elastic strain would be very tiny in magnitude. S dot we don't know anything about, so we can't get rid of it. So if we neglect these small terms, we would just be left with approximately a shifted version of S dot times the transpose of that shifter. Put that back in the derivative of the strain stress relation, and you get what you would expect right here. Okay, so this is the conventional expression of the Prandtl-Reuss equations. The total infinitesimal strain derivative, which is this, is equal to the dot of this elastic part in terms of the Cauchy stress, then the part that comes from the flow rule, like so. So you can think of this as the plastic strain, infinitesimal strain rate, and an elastic part here. And gee, I'm at the end of these notes and I don't have any more. So I think I'm going to have to let you go early today. So next time we will illustrate this system with some explicit examples that are, some of which are kind of interesting. And then we'll move on from there. Okay, so we have a shortened day today. We can all go back to watching the election. Okay. Any questions?
Yeah, can I ask you a question?
Sure.
I guess the only difference for the case of an isotropy is that we do not have the Lamé constants. We just have an arbitrary stiffness tensor with.
Yeah.
Okay.
Right. And also, we might have a plastic spin.
Yeah.
And we need a separate constitutive equation for that.
And this changes the flow rule.
Yeah, it changes the flow rule. So
okay.
The theory, there's virtually nothing in the literature about the appropriate version of the Prandtl-Reuss equations for anisotropy, because there wasn't sufficient advancement concerning plastic spin and things like that. So we'll talk about plastic spin and so on when we come back and talk about crystalline materials.
Okay.
We'll do that. I just wanted to cover this more classical version of the subject because there's a lot of solved problems there, and I'd like to discuss some of them.
Okay, thank you.
Yeah. Okay. If there are no other questions, then I will see you after the weekend. Right. Bye-bye.